We often think of scientific breakthroughs as being born from these really complex equations or maybe groundbreaking experiments. But what if some of the most profound aha moments actually come from something, well, simpler, something incredibly powerful, the scientific model? Today on the Deep Dive, we're exploring this fascinating world of models and modeling in science. And this isn't just about making little toy replicas, right? It's more
Yeah.
fundamental. It's about how scientists actually think, how they discover things, how they operate.
That's absolutely right. Models are, well, they're everywhere in science. They really guide our understanding from the tiniest particles right up to, global ecosystems. And
Mhm.
crucially, they play a really foundational role in how science itself is taught. They shape how students learn and grasp these often very complex ideas.
Exactly. We've really dug into the materials you shared, and our mission for this deep dive is basically to unpack these different kinds of models. We want to understand why they're so essential for scientific progress and, see how they shape our understanding of the universe and maybe even how we learn. So, okay, let's unpack this. Where do we start? What is a model in science, really? Is it just something that stands for something else?
Well, yes, at its core, it is something that stands for something else, but it's much more than just a picture or a representation. It's fundamentally a tool for action. Often it's a thinking tool, something scientists use to develop and test their explanations.
A thinking tool.
And a really crucial feature, maybe the most important one, is that models are always different from the thing they model. They're usually simpler or maybe different in specific ways that actually help the inquiry process. And this simplification isn't a flaw, not at all. It's actually a key strength.
Mhm.
It lets scientists focus on particular aspects of a complex system.
Right, that simplification lets you zero in.
Yeah.
And that can lead to some really compelling, sometimes even surprising insights. Yeah. Can you give us some examples? Where does this tool for action idea really come alive?
Oh, absolutely. Think about the Daisy World model. Remember that one?
Vaguely, yeah. Lovelock's Gaia theory.
Exactly. It was this highly simplified computer simulation designed to explore Gaia. It just had two kinds of daisies, black ones and white ones on a planet. Black daisies absorbed more radiation, warming things up. White ones reflected more, cooling things down.
Okay.
And as the model's sun got hotter over time, the balance shifted. More white daisies grew, reflecting more heat, and this kept the planet's temperature surprisingly stable. It basically sped up evolution massively in the simulation to show how these complex feedback loops could maintain stability even with external changes. It was a thinking tool.
Wow. Okay, so not predicting reality perfectly, but exploring a principle.
Precisely.
The
Or think about something more practical, like aerofoil testing in engineering.
wind tunnels.
Yeah. Engineers don't build a full-sized airplane wing for every single design tweak. That would be incredibly expensive and slow. Instead, they use scale models in wind tunnels. It's far more resource effective, lets them test and refine designs much faster.
Makes sense.
And even in medicine, modified surgical cadavers serve as models. Surgeons use them to develop new techniques or train novices. Obviously, the model is different from a live patient, but it allows for critical practice and development without any risk to a living person.
It's fascinating how they allow for that kind of action, that experimentation, without the full commitment or risk. And speaking of discovery,
Hmm.
maybe the most iconic example of using modeling, not just to show something, but to actually find it, is the DNA molecular model.
Mm.
Crick and Watson, you see those photos of the double helix, right? It looks like this perfect representation.
Mm.
But they didn't actually know the structure when they started building it, did they?
Not at all. That's a key point. They used modeling as a dynamic process to figure out the structure. It wasn't just building a replica of something already known. They were physically fitting components together, like a puzzle, guided by the data they had, things like the known ratios of the DNA bases, A to T, G to C.
And Rosalind Franklin's images.
And crucially, Rosalind Franklin's X-ray diffraction images. That data provided constraints. Their modeling approach, while Linus Pauling had dabbled in it, was quite novel for its time. But now, it's standard practice in fields like pharmaceutical research. They use computer simulations to explore millions of potential drug compounds before they even think about making them in the lab.
That really drives home how the power of a model isn't just in what it looks like, but in how you use it. Which brings up a tricky point, doesn't it? When does a representation actually become a model? Like take a chemical equation, P4 plus 6Cl2, 4PCl3. Is that a model? It represents a reaction.
Well, that's where it gets interesting. As you say, it is a symbolic representation, yes. But because it represents the reaction in a way that lets you do calculations about the real chemical system. like figuring out how much chlorine you need to react with a certain amount of phosphorus. Its status as a model really depends on how it's understood and used. It's not just an inherent property.
That's about the function.
Exactly. And that distinction actually goes even deeper. It connects to basic linguistic tools we use all the time, like metaphors and similes. They're surprisingly foundational to modeling.
Metaphors and similes. How so?
Well, metaphors suggest one thing is another, even if it's not literally true. Like when we say the cellular nucleus is the brain of the cell.
Right, the nucleus isn't actually thinking.
No, of course not. But the metaphor helps us grasp its role in controlling cellular activities. It directs things.
And similes are more explicit then, like saying something is like something else.
Precisely. The nucleus of the cell is like the brain. Or that classic one. An enzyme fits substrate molecules like a lock and key. It explicitly states the similarity.
Got it.
And adding another layer here, scientists often use these generic terms, like the cell or the atom. These are basically conceptual models for a whole class of things. Think about the dog is a four-legged animal. That's our general model or concept of a dog. It still holds true as a general statement even if we meet a specific dog that unfortunately lost a leg. We're talking about the type.
Ah, okay. The idealized version?
Sort of, yes. And then you have what are called dead metaphors. These are fascinating.
Dead metaphors.
Yeah, terms like electron sharing in chemistry for covalent bonding or electron spin. These started out as figurative language analogies, but they've become so embedded in scientific language that they're often treated as literally true. Chemists know atoms don't literally share things like people do.
But the term sticks.
Exactly, and it becomes part of the accepted scientific description.
That must be tricky for students, though. If a term started as like something, but now it just is that thing in the textbook.
It absolutely is a challenge. If learners aren't aware of the original figurative nature, it can lead to real confusion down the line. They might take it too literally.
Okay, so from these linguistic roots, we move towards more formal analogies.
Right. Analogies involve a more explicit, structured mapping between two different systems or domains.
Can you give us a powerful example of that in action, something that really pushed science forward?
A great one is the liquid drop model of the atomic nucleus.
Liquid drop for an atom's nucleus.
Yes. Lise Meitner and her nephew, Otto Robert Frisch, used this analogy back in the late 1930s. They were trying to understand some puzzling experimental results, which we now know as nuclear fission. They imagined the nucleus behaving like a drop of liquid. If it absorbed an extra particle, like a neutron, it might become unstable, wobble, and then split into two smaller droplets.
Just like a cell dividing.
That was part of the analogy, yes, by analogy with cellular fission. What started as maybe a simple comparison became a really sophisticated scientific model that helped them visualize and explain this brand new phenomenon, nuclear fission.
That's incredible. And this ties into mental models too, right?
Yeah.
Scientists doing thought experiments.
Absolutely. Einstein's Gedanken experiments are famous examples running simulations entirely in his head. Or Temple Grandin, who designs humane livestock handling systems. She talks about testing her designs by visually simulating them from the animal's perspective, imagining being a cow going through the system.
Wow.
Even things we take for granted, like Michael Faraday imagining magnetic field lines, or physicists drawing light rays in optics, these are useful mental tools, mental models, that help us represent and reason about real physical systems.
And for you, the listener, it's worth remembering, we all form mental models to understand the world. The catch is, research shows our everyday mental models are often quite different from the scientific ones. Like, a child might think day and night happen because the sun literally goes behind a mountain. It's a model, but not the scientific one.
Exactly. And that brings us to a really critical point about analogies. They have limitations. They have what we call negative features.
Negative features, meaning parts that don't match up.
Precisely. Only some aspects of the analogy map correctly onto the target system. Let's take that classic school analogy. The atom as a miniature solar system.
Bohr model, right. Nucleus like the sun, electrons like planets.
Yes. It has some useful mappings of the positive features. There's a central body with most of the mass and things orbiting it. That helps visualize structure. But the negative features, the parts that don't work, are significant. Electrons are all identical, unlike planets, which are varied. Electron orbits in quantum mechanics are stable energy levels. They don't decay like planetary orbits would due to energy loss.
And the forces are different too, right? Electrical, not gravity.
Completely different. Electrical forces in the atom, gravity in the solar system, plus electrons repel each other, whereas planets gravitationally attract each other, albeit weakly.
So lots of ways it breaks down.
Indeed. And there are even neutral features, things in one system with no parallel in the other, like planets having moons. The atom model just doesn't have an equivalent for that.
This is so important, especially for anyone listening who teaches or learns science. You have to be explicit about the limits of these analogies, don't you? Otherwise, students could walk away with really fundamental misconceptions.
Absolutely crucial. They might end up thinking gravity holds atoms together or that electrons whiz around like tiny balls, which just isn't the modern scientific picture.
Okay, which leads us nicely into the role of models, specifically in science education.
Yes, they play a really interesting dual role here. First, education needs to reflect the authentic practice of science, and modeling is central to that practice. So teaching about models is important. But second, models themselves are vital pedagogical tools. They help students actually learn the complex concepts.
That makes sense. So much of what's taught in science, especially at higher levels, is theoretical, isn't it? It relies heavily on models because we can't directly see atoms or molecules reacting, like reaction mechanisms in chemistry. You mentioned SN1 and SN2 reactions earlier. Those diagrams with arrows showing electrons moving.
Exactly. Those are models. They represent hypothetical sequences of events at a submicroscopic level. They're inferred from indirect evidence, like what products are formed under different conditions. No one has ever seen an individual molecule go through that exact SN1 process. Students might easily assume those diagrams are like snapshots of reality, but they're explanatory models built to fit the evidence.
Right. And even classifications, you're saying, can act as models.
That's another fascinating area. Scientific typologies often function as models. Think about classifying chemical elements that's relatively clear-cut now with the periodic table based on atomic number. But what about classifying elements as metals versus nonmetals, or defining strong versus weak acids, or even the biological concept of a species?
Those lines can be fuzzy sometimes.
They can. These classifications involve making judgments, simplifying the inherent complexity and continuity of nature. There are always edge cases. Is nitric acid truly a strong acid? Well, for most school purposes, yes. But technically, its dissociation isn't 100% complete, so chemists might describe it as almost strong. It highlights the simplification. Same with species. The concept works well generally, but evolution means species change over time, and you get ring species or hybrids that blur the lines. The classification is a useful model, but it simplifies a dynamic reality.
And students often struggle with this, right? They might have a very naive idea of what a model is. I know I probably did. Like thinking only of those physical scale models, the plastic torso in biology class, or a model car.
That's very common. Research shows students often start with this model equals scale replica idea. And while those physical models, like the torso, are useful teaching aids, they're massive simplifications. They leave out all the connective tissue, the fascia, the complex networks of nerves and blood vessels.
Things a teacher might just assume students know are missing, but they might not.
Exactly. And the crucial point is, a model only functions as a model for the learner if they understand how it relates to the target system, what it represents well, and what it simplifies or omits.
Okay, so understanding the model as a model is key.
Yes, and this is why teaching even scientifically outdated models can be okay if done carefully. Take the orbital atom model, the Bohr model again.
Still taught in schools, isn't it?
Often, yes. Because it's useful for explaining certain concepts at an introductory level, like electron shells and basic valency. But scientifically, it's been superseded by quantum mechanics for decades. The danger is if students come to see it as a literally true picture of the atom, a realist understanding, because that can actually hinder their ability to learn the more advanced and often counterintuitive quantum model later on. The models are incompatible in many ways.
Wow, so a model that helps initially can become a barrier later if not handled right. It almost sounds like models can sometimes trap thinking, even for scientists.
They absolutely can. It's a known phenomenon. Scientists themselves can get stuck because they become too attached to a particular model, assuming it's the complete truth. A famous example is the central dogma of molecular biology. For years, the standard model was that genetic information flowed strictly one way. RNA makes protein.
DNA, RNA, nice protein, I remember that.
Right. It was a powerful and useful model, but it became so widely accepted, almost treated as absolute law, that it may have discouraged some researchers from even looking for exceptions. Then came the discovery of reverse transcriptase, an enzyme found in certain viruses, like HIV.
What did that do?
It showed that RNA could actually be used as a template to make DNA. Information could flow backwards, from RNA to DNA.
So the dogma was wrong. or incomplete?
Incomplete. The basic flow is dominant, but the model needed revising. It showed that even a really successful model could limit thinking until new evidence forced a change. It also ties into theories like the RNA world, suggesting RNA might have been the primary genetic material early in life.
That's incredible and really highlights why what you called an authentic scientific education needs to put models and modeling front and center. It means being really explicit about the status of the models we teach, what they're good for, where they break down, exploring strengths and limitations.
Exactly. And in education, it helps to distinguish between two types of models. There are curricular models.
Okay, what are those?
These are essentially the simplified versions of current scientific models that we choose to teach at different levels. They're designed to be appropriate for learners' understanding and act as stepping stones to more complex ideas later. The Bohr-Adam model, when taught appropriately, is a curricular model.
Got it. Simplified science for teaching. And the other type?
Teaching models. These are different. They are models developed specifically for pedagogical purposes, often with no direct counterpart in scientific research itself.
Ah, like demonstrations.
Often, yes. Think about using a simple globe and a lamp to demonstrate day-night cycles and seasons. The globe is a physical model, simplified, not perfectly to scale, but it gets the concept across clearly.
Or that model mine you sometimes see in physics classes. The box with two chimneys and a candle underneath one.
Perfect example. You use smoke to show how the candle heating the air creates convection currents, drawing air through the box. It's a model of convection using a mine shaft context designed purely to teach that principle.
And the classic model lungs. Balloons in a bell jar with a rubber sheet at the bottom.
Another great one. It's dynamic. It shows how the diaphragm contracting increases volume and draws air in. But anatomically, it's way off, isn't it? The balloons are tiny compared to the jar. They're surrounded by air, not fluid.
So how should teachers handle these teaching models that are kind of inaccurate but show a process?
The key is, again, explicitness. A good teacher might use the balloon model to show the mechanism of breathing, but then immediately contrast it with anatomically accurate diagrams or maybe animations to show the actual structure. Use a range of models, and always discuss the strengths and weaknesses of each one. What does this model show well? What does it distort or leave out? We've actually seen studies where students engaged in critiquing these kinds of pedagogic models, like analogies for electric circuits involving vans delivering bread or water pipes or even students walking around a circle.
Those analogies always felt a bit strained to me.
They often are, and they have significant limitations. But the process of students thinking critically about why the analogy works in some ways and fails in others, that process is incredibly valuable. It mirrors how scientists themselves evaluate and refine their own models. Even though the bread vans aren't a scientific model, thinking with and about the model is scientific thinking.
That's a great point. So
Yeah.
the critical thinking about the model is key, but teachers absolutely have to make it clear which models are just teaching tools and which ones actually represent current scientific understanding, even if simplified.
Couldn't agree more. That distinction is vital. And then moving beyond just using models provided by the teacher or textbook, there's immense value in getting students to create their own models.
You mean more than just building a scale replica, right?
Yeah,
Like
right.
that model cell made of sweets or plasticine.
Yes, exactly. While those activities can be fun and help visualize parts, true scientific modeling is often more abstract. It's about developing a representation, maybe a drawing, a diagram, a concept map, even a simple mathematical relationship to explain a phenomenon or solve a problem.
It taps into creativity, doesn't it? Science is often portrayed as purely logical, rational.
And it certainly involves logic. But creativity is just as crucial. The ability to imagine possibilities, to generate novel representations, to think analogically, that's at the heart of scientific discovery. When students are tasked with building, developing, testing, and refining their own models to explain something, it offers them a genuinely authentic scientific activity. It engages them deeply and lets them experience firsthand how imagination fuels scientific progress.
So pulling all this together, what's the big picture here? What does this all mean for how we should think about science?
Well, I think the main takeaway is that models and modeling aren't just some niche aspect of science. They are absolutely central. They are essential thinking tools. They are core explanatory devices. And if we want an authentic science education, one that truly reflects how science is done, we have to emphasize the nature of models, explore their limitations explicitly, and ideally get students involved in the creative process of modeling themselves.
Yeah, understanding models really changes things. It's not just about memorizing scientific facts anymore. It becomes about understanding how science works, how that knowledge gets built and refined. And it's about being able to tell the difference between a useful simplification and, the messy reality it represents. It makes you a much more critical thinker about scientific claims. So maybe a final thought for you listening.
Mm.
Next time you come across a scientific explanation, could be in a textbook, could be a news report, maybe just in conversation. Try taking a moment. Ask yourself, what's the underlying model here? What is this explanation built upon? And what might its strengths be? But also, what might its limitations be? Where might it break down? You might find yourself looking at the world and the science trying to explain it in a completely new light.
Absolutely. And that journey of understanding models, appreciating their power and their pitfalls, it's really a lifelong pursuit. There are always new connections and deeper insights to find.